Hello everyone, let's talk about exponential growth and decay. This is something that you guys do a little bit in algebra, but we're going to hit it again. And first thing you need to realize is you've got this formula here, and I'll go over the parts of this formula. P is the principal, that's how much money you're starting with. It can be a loan or it can be an investment, but that's how much money you're starting with. R is the interest rate. Now that needs to be expressed as a decimal. So remember, 5% is 0.05. It's 5 out of 100. 5/100ths is 0.05. N is the number of intervals in a year that you will compound the interest. And then T and N times T, it kind of depends on the context, but usually it's how many intervals times how many years. Okay, usually that's how it works. Essentially, this is how many times you will need to compound the interest. So let's go through one here. Create a college savings account for Benny, and I'm going to say this is an aggressive rate of return at 8%. Okay, that's pretty good. If you get 8% every year, you're doing all right. He deposits $2,000. So the idea here is I'm going to put $2,000 into an account, and then I'm not going to do anything with it. I'm just going to let it sit there and accrue interest. Okay, and this is something that I've done. I've created an account for Benny. So let's start with $2,000, and then I'll say 1 plus R, the interest rate, 8% is 0.08. And if you do something annually, the number of times that you do it in a year is once. Okay, there's 1 year in a year, so you do it once if it's annually. Now, this part, N times T, if you do something once a year for 18 years, that will be 18 times we will compound the interest. Okay? So this is very much calculator work at this point. So we'll get a calculator going. All right. And now I'm going to say $2,000. 1 plus, now the interest rate is 0.08, and I'll type the divide by 1 because it'll just make it easier for the next time, to the power of 18. And that means that there are now 7,992, and it's money, so 0.04, $7,992.04 in the account. Okay. Again, I didn't add to it. After the first investment, I just put $2,000 in there, and then I just forgot about it. And I almost quadrupled my money. I'm almost at $8,000, which is nowhere near enough money to go to college. Okay, but this is a $2,000 investment. So I still did a good job quadrupling my money. Now, let's see if it's different if you compound it quarterly instead. So this will be $2,000, same thing, 1 plus 0.08. But now, instead of doing it 1 time a year, I'm going to do it 4 times a year. Quarterly means 4 times a year. But what you should notice is you're not getting all 8% 4 times a year. You're getting 8% divided by 4. So you're essentially getting 2%, but you're going to compound the interest more often. If you do something 4 times a year for 18 years, 4 times 18 is 72. So we're going to do this 72 times now because it's 4 times a year for 18 years. How will that affect the whole thing? I'll just take this guy and I'll change this to 4. So now we're doing 1/4 of the interest rate, but we're doing it 4 times. 72. Okay. 8322.28. 8322.28. Now, you might think, wait a minute, you made more money compounding the interest differently? You do. You make slightly more money compounding the interest differently. I actually made about $400 more, just shy of $400 more than doing it annually. So based on that, should I expect to get another $400 if I do it monthly? Let's find out. 2,000, 1 plus. Now you're getting 1/12 of the interest rate, but if you do something 12 times a year for 18 years, that's 216 times you're compounding the interest. So 2,000, 1 plus 0.08 divided by 12, and now I'm compounding the interest 216 times, so that is 8401.15. 8401.15. So wait a minute, that was only like an $80 difference, and that's how this works. When you compound more often than once, you're going to get a pretty decent gain. But the more often you do it, that gain starts to slow. There's an asymptote to how much money you can gain. If you do it by the second, that's going to be about the same as if you do it by the hour. And I'll talk more about that here in a little while. But basically, you just have to fill in the formula and then type in the calculator. If you can do that, this is not bad. Okay, this says you buy a new car for $23,000. And now this word depreciates. That means the value goes down. So we're going to use the same formula, 23,000, but now it's going to be 1 minus instead of 1 plus. and it's 21% each year, so we'll do 0.21, and we're assuming it's annually. And if it's over 5 years, it's going to look something like this. Okay, once a year for 5 years, 1 times 5. So 23,000. 1 minus, if you didn't realize this, every time you buy a car, your value decreases when you drive off the lot. That's called depreciation. That is now 7077.23. 7077.23. So you bought yourself a $23,000 car, you drove it around for 5 years, now that car is worth about $7,000. That seems pretty reasonable depending on the type of car you have. Okay, 5-year-old car. The used market's a mess right now, so. But it should definitely be less than it started with. Depreciate means it goes down. All right, let's watch this. Okay, I'll set this up. This is a show called Futurama. It's an older cartoon, and the idea is the main character's name is Fry. He gets frozen 1,000 years. He gets frozen in the year 2000, and he wakes up in the year 3000. And so what we're going to talk about is how much money would be in his bank account. So let's see if I can find this. I have it right here. Okay. So let's watch. It's only 1 minute.
Do we have enough money to pay Bender's fine?
78, 79, 79.50. Crud. We're 50 cents short.
I'd love to chip in, but Bender stole my wallet.
Hey, that's my old bank. Maybe my account's still open.
We don't seem to have your retina scan,
have
your
Face ID.
fingerprint, or your colonic map
They have
on file.
fingerprints.
Yeah, well, I did open
That's
the
the
account
future.
over 1,000 years ago. What about my ATM card?
Do you still remember your PIN number?
Sure. It's the price of a cheese pizza and a large soda back where I used to work. Panucci's Pizza.
Okay, you had a balance of 93 cents,
All right.
and at
I
an
love how
average
he's
of
not
2.25% interest over a period of 1,000 years.
Okay, 2.25 interest, 1,000 years. So 93 cents, 2.25 interest, 1,000 years. So if I do this annually, we'll say he starts with 93 cents. I just love how he's not broke. 1 plus 0.0225. You got to move the decimal twice, so there's going to be a 0 in there. Once a year for 1,000 years. So let's get my calculator out. 0.93, 1 plus 0.0225, and now to the 1,000th, because it's 1,000 years. A big number. Let me go back. I'm going to see if I can read this number. It'll be easier. Okay. So let's see. Comma. Wait, no, missed. 1, 2, 3. There you go. So 4.28 billion with a B. Billion. $4.28 billion. He had 93 cents. Now he has 4.28 billion. Let's see if the Futurama people can do math. I'll do that last part one more time.
You had a balance of 93 cents,
All right.
and at an average of 2.25% interest over a period of 1,000 years. That comes to $4.3 billion.
4.3, 4.28, 4.3 billion. We got it. Okay, let's do the same thing with semi-annually and see how big of a difference it makes here, because I bet this is going to be crazy. So semi-annually means you do it twice a year, and if you do it twice a year for 1,000 years, that's 2,000 intervals. I don't need that anymore. Okay, so give me my calculator. So 0.93, 1 plus 0.0225 divided by 2 to the 2,000. So that's $4.85 billion. So what's $500 million? What's $500 million in the grand scheme of things? If you compound the interest just slightly differently, you get a lot more money. And I'm not going to do the same thing with monthly and daily because I want to just keep this thing moving. So let's talk about now so this says the financial world doesn't compound interest annually. So your bank account is constantly moving in and out, and they have a slightly easier version of this formula, and it has to do with the idea that you're breaking up the time into smaller and smaller intervals. And we have this number called Euler's number, which is on your calculator. E is on your calculator right here. So if I do e to the first, every calculator should have an E button. It's 2.71-ish. E is kind of like pi. It's an irrational number. It goes on forever. It doesn't have a decimal. And it's used quite a bit in science and finance and those sorts of things. So If you change the formula using e, you get rid of that 1 plus 1 over part, and you just put an e right there. And now we have r times t, so the interest rate becomes part of the exponent now. So this is slightly easier. I call this the PERT equation, P-E to the RT. $5,000, E is that number, and then it's 0.02, so 2% interest for 5 years. So to do the same thing but compounding continuously, 5,000 E to the 0.0202 times 5 is 5525.85. 5525.85. So if you compound it continuously, you'd make 5,500. Let me show you how it would look if we did it annually, and hopefully you realize that it's going to be much less, because the more you compound it, the closer you get to this e value. 5,000. 1 plus 0.02 divided by 1 doesn't matter, to the 5th power. 5520. So see how it's a little bit different? It's not a lot. It's not a huge amount of money, but it is different. So it is going to be slightly different if you do it continuously versus if you do it annually or semi-annually. So there's basically 2 ways you can compound interest. We can do it in these intervals, or we can do it what we call continuously. And the last thing we'll do is population. We'll do this one continuously, because we just learned that formula. Again, P-E to the RT. So this says the world population has grown exponentially. It has. Anything that is a change from the previous amount is exponential, and it's about 1.25. So if we start with 1.7 billion people, and we say 0.0125, from 1900 to 1958 is 58 years. So we compound the interest, 1.7 e to the 0.0125 times 58. I don't really know how many people there were back then, but it's about 3.51 billion. Now, think about that. In that person's life, they were born in 1900, and then in 1958, so they're about 60 years old, their population has doubled. The world population has doubled in their lifetime. Let's see how it is now. So we're still starting in 1900, 0.0125, but now, if this is from 1900 to today, we'd say 2024 is 124 years. So what should we expect the world population to be based on this model? E, 1.7, E, 0.0125 times 124. It should be about 8 billion. That's pretty good. We'll say 8 billion, which is, we just hit the 8 billion mark in 2023. So, okay, think about that. If you were alive in 1958, so if you're born in 1958, you got, let's see, 2024 minus 1958, so 42 plus 24 is 66. You're 66 years old. The population has more than doubled in your life. It would be about 7 now. It's over that. Now let's use the same model to kind of predict what would happen in 2050 from 1900 is 150 years, 1.7 e to the 0.025 times 150. How many people should we expect in 26 years? 70, no, I typed something in wrong. That can't be right. It's 0.0125. Yeah, I'm like, that's too much. 0.0, can I do this? Insert a 1. There we go. Okay, that's a way too big of a number, so I knew something was wrong. 1.7 e to the 0.0125, there we go, 150. 11.08. 11.08 billion. So in our life, in the next 26 years, we're going to see about 3 billion people. So that is 26 years we see 3 billion. In this person's life, they were 66. They saw more than 3 billion. They saw closer to 4 billion, almost 4.5 actually. Okay, so you guys have a problem you're going to need to address. And that's pretty much how exponential growth works. And what you need to do is, first of all, do the practice problems, and secondly, smash that like and subscribe.